Hi everyone, this is Chen from PUC-Rio de Janeiro. Today I would like to share with you our recent work on this issue of measurement of topological order based on a concept that we propose that we call metric-curvature correspondence, which is a very general principle that is applicable to any topological order in any dimension in symmetry class. So to begin with, I would like to make a sort of quick review of what is going on about these topological materials, including the concept of symmetry classification, which actually I have already introduced in the earlier videos. So there contains more details if you're interested. But here, let me briefly go through this. So these topological materials, they contain they are usually well described by these Dirac models, which contains a conduction band and a valence band. And they can be multiply degenerated. And the Dirac Hamiltonian, as described as such, can be classified according to their symmetries, namely the time inversal, particle Hall, and chiral symmetries, defined in this manner. And it is well known that these symmetries classify 10 symmetry classes for all the topological materials, and each of them would also belong to a different dimension. And these Z and Z2 and 2Z are the topological invariants that describe each dimension in symmetry class. In a recent work, we have proposed a universal topological invariant for any one of these elements in this table, or any one of these elements in this table that we call the Repping number. So the Repping number is constructed in this way. So we start from the Dirac Hamiltonian, which has these D vectors that characterize the components of the momentum dependence on every component of the Dirac matrix. Now you can construct a unit vector that we call n of k, which is this d of k divided by its module. And then you do the following. You say that you construct the cyclic derivative of this n vector. You take its n components, every component of it. In d dimensions, there's a d, there are d plus 1 components of them. And then you take a spatial derivative of them and combine it in this fully anti-symmetric way that we just collectively call them cyclic derivative of n of k. You integrate them all together, and this is usually called the degree of the map, or also what we call the Repping number. And the claim is that this is the universal topological invariant for any Dirac models. Using this lattice model of 2D Chen insulator as an example, that whose Hamiltonian just contains the three components of the Pauli matrices. And in the simplest lattice model, they are characterized in this way. Yeah. Now you can actually visualize this n vectors in the following manner. Let's say because the Brillouin zone is 2D in this case, so you can visualize them as these small unit vectors in the Brillouin zone. And you can collect all the base of these blue vectors together to form what we call the Dirac sphere. Then you see that in the first case, when the mass term m is positive 1, all these d vectors, all these n vectors together, pointing roughly to the north pole of this Dirac sphere. Whereas when m is equal to -1, you have some components that are pointing to the south pole. And therefore, if you collect all these blue arrows together, they're going to wrap around the sphere once. So this degree of the map, or the Repping number, is essentially counting how many times that these blue vectors wrap around this Dirac sphere. Now, yeah, and it has been shown in our recent work that all these topological invariants known on this table can be cased into this symbol form, and therefore we have a sort of very nice unification of all the known topological invariants, including quantized Hall conductance, Majorana numbers, charge polarization, and all these that you are familiar with are all here. Now, besides this, our recent work is to further clarify this relation between this cyclic derivative of the n vector and another very important concept in the issue of quantum information and quantum phase transition, namely the so-called quantum metric. So quantum metric is the following idea. You start from the Dirac models, which, as I say, they can be, they have conduction band and valence bands, and in general can be multiply degenerate. Yeah. Now all the valence band states are filled because you have because they are fermions, and you take all these field band states, you construct a fully anti-symmetric state because this is supposed to be a Fermi C, right? And a momentum K. Then you calculate the so-called quantum metric, which is often also called fidelity sensibility. That is defined in the following manner. You take this quantum state that is defined in some momentum, and you take it to make an inner product with exactly the same state, a slightly different momentum K plus theta K. And then you write the module of this thing as 1 minus 1/2 of G mu nu times this small displacement, which to leading order, you can prove that it must be quadratic. And this way you immediately defines so-called quantum metric, which takes this explicit form here. But physically, you can visualize it in this way, because this psi of K, which is the field band state of the Dirac Hamiltonian, right? So it is like a small vector in the Hilbert space that I'm drawing here. For instance, here I have a Hilbert space of 3 basis vectors. And then you can imagine that when you change the parameter from K to K plus delta K, then this unit vector is kind of rotate a bit in the Hilbert space. So because they are both unit vectors, so the dot product of them must be less than 1. So you write it as 1 minus some corrections. And these corrections will naturally define the quantum metric. Now, particularly for Dirac models, after some algebra, you can also prove that these D vectors, this quantum metric are actually simply given by the derivative of these n vectors, which parameterize your Dirac Hamiltonian. Yeah. Now, given this, you can actually do further calculations. So this degree of the map, as we have introduced earlier, is calculated from this Jacobian, which is this fully anti-symmetric combination of this n vector and the derivative of this n vector. Now, the square of this Jacobian, if you calculate the square of this and write it in this manner, then you see immediately that it is also equal to the determinant of this derivative of the n vector dot product together. So this immediately means that the module of these Jacobian is exactly equal to the square root of the determinant of the quantum metric. Yeah? And this relation, we call it metric-curvature correspondence. And as I say, this is because the wrapping number is valid in any dimensional symmetric class, and so is this simple formula here. Now, the significance of this formula is that it means if you can directly measure this quantum metric and calculate its determinant, then you can directly measure the Jacobian here, and therefore possibly can give you the information about this degree of the map. In other words, the topological invariant. So our goal will be to sort of propose a protocol that you can measure this quantum metric and in topological insulators, such that you can in turn directly measure this topological invariant. Although I should emphasize that here, all you can measure is the module of this Jacobian, whereas you cannot fix the sign of it. So strictly speaking, you still cannot rigorously obtain what is the degree of the map. But nevertheless, locally, at least you can give some information about how this magnitude of the Jacobian has some regions in the momentum space, which is still very good. Now, to come up with a measurement protocol, we use this time-dependent perturbation theory pioneered by Ozawa and Goldman, which is the following idea. Suppose you have a Dirac Hamiltonian, right? Let's say a 2D version, such that you have kx and ky here, and this is a field band, this is an empty band. Now, the theory says that if you apply a pulse electric field, polarized pulse electric field along mu direction, and with some envelope shape, right? Let's suppose this is the pulse electric field that you apply. That is the shape that we call G of t. Then the time-dependent perturbation theory tells you that the magnitude after this pulse is applied, some electrons in the valence band will be excited to the conduction bands, and this you can measure by time-resolved RPES. Yeah, and this number of particles that has been excited to the conduction bands after the pulse has been passed will take this formula. Namely, it will be the strength of this field times the Fourier transform of this envelope function, and then multiplied by this part, which will turns out to be exactly the diagonal elements of the quantum metric. And then the idea is that once you apply a certain pulse and then you kick some electrons out of the conduction band, and you can measure how much you have kicked them out to the conduction band using time-resolved RPES. Because time-resolved RPES can tell you that how many electrons are missing in the valence band, or how many electrons are actually promoted to the conduction bands. So we have kind of loss fluence spectroscopy, where the loss is the loss of particle number in the valence bands. The fluence is the intensity of this light times its duration, basically. Yeah. And also using some other tricks that I will not explain it to you here, but you can also measure the off-diagonal elements of the quantum metric using some polarized light. Now, to make a concrete estimation, we use graphene as an example, where the topological order in graphene goes like the following. Graphene contains two Dirac points, which you usually call k and k prime. If you take the wave function and calculate this combination, the so-called Berry connection, in other words, you take the eigenstate and take a derivative of it along a certain trajectory in the angular direction. And the claim is that this integration will always be a quantized number, and it will be of opposite sign between k and k prime points. Now, the metric curvature correspondence in this case of graphene will be exactly that. You're going to take this derivative of the eigenstate, the module of it, or you can take the square root of it. It's the same thing. That will give you the value of 1/4. So in other words, if you can manage to measure that the quantum metric along the circular direction, along the angular direction, surrounding each k and k prime point is a constant meaning a constant independent of how big is this loop. If you can prove this, then this will mean that you have observed the topological charge of the near k and k prime point. Now, we estimate that this is entirely possible using this time-dependent perturbation theory that I was explaining to you in the previous slide. Our estimation is that if you apply a polarized electric field where the field strength times the duration of the time gives you the so-called fluence of the order of 10 to the -4 millijoule per centimeter square, then you can cause an excitation roughly of 10%. So in other words, after this pulse is already passed, roughly 10% of the electrons will be promoted to the conduction band of graphene, yeah, which is entirely feasible. And in fact, this kind of experiment is already done in graphene, where, for instance, in this Gersdorff experiment, where they use exactly what we are saying here, some kind of duration of the pulse, and then promote some electrons from the valence band to the conduction band. As you can see here, this is RPES spectrum function right before the pulse is applied. during the pulse and then right after the long after the pulse has been passed. So indeed, after some 30 femtoseconds after the pulse has passed, you see that there's a huge weight that in the valence band that has been reduced. So in other words, they have been kicked to the conduction band. So in other words, if you can quantify how much this reduction is against how much fluence of a light that you have applied, then you can actually be able to measure the quantum metric and give you the direct information about the topological order in graphene. Yeah. The only message to experimental is that this experiment, as far as we know, is not using polarized light. So for our purpose, then the light source has to be polarized. And that's it. Thank you very much for your attention. If you have any questions, please don't hesitate to contact me. Thank you.